Yes,
Yeah.
I think you can start.
Okay, so today I'm going to do an introduction to the cake cutting problem, which is a social choice problem where the goal is to cut a cake between n agents and to do it fairly. And we will see what it means to do it fairly. So yeah, you have a cake, a birthday cake, and actually consider that your cake is heterogeneous. So on the top of the cake, you not necessarily have something that is, there is some noise. I don't know if someone forgot to cut their mic or. Okay. So yeah, you consider that your cake is not the same everywhere and that your agents may not necessarily have the same preferences. So for example, here you have like red fruits and green fruits, and you can consider that maybe some agents do not like fruit at all. Some prefer the red, some do like both. And the goal is really to separate the cake and to share the cake so that everyone is happy. And for example, you could consider that you have 5 agents and that this is a possible cutting of the cake. So you don't necessarily need that the parts have the same size. What you want is really to maximize the happiness of everyone. And to do so, so you have this cake. You will assimilate the cake to the interval 0, 1. So this will be the model we use. And so if you cut the cake like this, you just consider that this will be a part of the interval 0, 1. And also in the model we consider, we want to share the whole cake. So we don't want any remaining part. We really want a partition of the interval 0, 1. And yeah.
So you consider that the first cut is always in the same place, right? Because you have 4 cuts on your interval, but they're sort of cut at 0.
So you just assume that one of the point here is the start of the interval 0, 1, and that this is the interval.
So the horizontal cut is.
Yeah. You just do this arbitrarily, but you actually allow that when you cut, it's not necessarily each agent will not necessarily receive an interval that is not an agent can have a group of intervals as their part. So that's why it doesn't count in the model here. It's not important. Yes?
Just to understand the model also, in your drawing, you have some things on the cake.
Yeah.
Does it play a role in the way you does it add some values of the part?
So in the model, it has a role in the sense that the agents will have preferences based on what is on the cake. Yeah. So it will just influence the preferences of the agents. But you will see that the agents, their preferences are modelized as a measure on the interval. And so once you have different measures? Yes, they have different measures. And when you know the measures of the agents, you forget about what the cake looked like at the beginning. Okay, so that's for the model. And as I say, so the cake C is the interval 0, 1. There are n agents, and each agent has their own preferences that is modeled by a measure mu I on the interval 0, 1. This represents their utility, so how they evaluate the cake. And so each measure has some properties. So it's defined on all finite units of interval. It's non-negative. This is just for practical reason. We consider that each agent has still a positive, is still happy with the piece of cake, and that they cannot be not happy with having a piece of cake at the end.
It's not allergic.
Yes, they are not allergic to the cake. Each measure is additive. This will be useful when we will see algorithm to allocate piece of cake. We will see that this is useful. Divisible is just to say that you don't have atoms, I think. So you don't have every measure is such that you don't have one point that is evaluated at 1 and the rest 0. You cannot have that. It's continuous, and it's normalized. This again, it's not necessary, but it makes the calculations easy and the intuition easy as well. So that's why we consider probability measures. Okay. So yeah, so now we can see, yeah.
For divisible, it means that there is no Dirac.
Yes, that's it. There are no
general distribution, just standard.
Yeah.
Just for me to be sure that it's just remove this.
Yes, that's it. We have no Diracs, and actually, if we would allow Diracs, there are theorems that would not hold, and I will explain later. Yes.
The measure takes into account the ingredients or for the moment.
The measure takes into account one.
Ingredients.
Um,
Yeah, right. It's
yeah.
the amount of ingredients, more or less, that are in the part of the cake.
It's how much individual appreciates each part of the cake.
Yes. So of course, yeah, depending on the ingredients of the cake,
Okay.
there will be different. But once you have the measures, you consider that you know every measure for every agent, and then you just forget what the cake looks like. So yeah, so there is a comment. Sorry. Oh, okay. Yeah, so the first notion we can think of is what we call equitable. So for every agent, agent I, for example, thinks that their piece of cake is the same value as agent A. Like both agent I and J have the same level of happiness for their piece of cake. This measure is not very used in the literature. It has not very been studied, and there are two reasons. The first reason is that here everyone could be not very happy with their piece of cake, but as long as everyone has the same level of happiness, this still holds. So, for example, you could everyone could have a utility 0.1 here, and this could still hold. So that's the first reason. And the second reason is that there are agents that could be envious of other agents. So here, the utility I assign to my cake is the same as my friend utility assigned to their piece of cake. But I could think that the piece of cake of my friend has a better utility than mine, because here it's mu j of cj and not mu I of cj. And so this leads to the second notion of fairness, which is envy-free. This is just to say, I am not jealous of anyone else. So the utility I assign to my cake, I think, is greater than the utility I would assign to everyone else's piece of cake. This is a very intuitive notion, and also it has been studied a lot in the literature, and we will see algorithms that allocate envy-free piece of cakes. There is another notion which is called proportional. This is a bit relaxed compared to envy-free. It's easier to get. And this is just to say that every agent consider that their piece of cake is greater. The utility they have is greater than 1 over n, which is the average. Yeah, the average I would allocate to the piece of cake, because mu I of c is 1. So in average, they are happier than what they would have in average. Is it clear for everyone?
I don't understand the equality.
So, for example, if there are 3 agents, oh, this one. This is just to say.
One, because you normalize, so 1 over n is just the value of the cake divided by n.
You don't
No,
understand
C,
this
no,
equality?
I didn't see, C is the one, yeah, no, it's
Yeah.
oh,
Mu I of C is always one. Yeah.
In my mind, there was a I index, it is not real. It's okay.
Oh, okay, yeah. See, this is mu I of C, so yeah, the whole case. So yeah, this is just to say my utility is better than the average utility. And yeah, and I put those next to each other because there is another notion, which is K proportional, which we will see englobes those two notions. So this is when you have a set of agents of size K, the utility I assign to my piece of cake is greater than the average utility on this particular set of agents K. And this is true for every set of agents K. So for example, you can see that when K is equal to N, this is equivalent to proportionality. Okay, for every set of N agents, so for the whole set of agents, the utility I assign is greater than the average utility. Okay. And yeah, so this I said, yeah.
And when K is equal to 1 is equal to envy-free.
No, not 1, but when it's equal to 2.
2.
Yeah. As for all I in J. Yeah, you're right. For all I in J, I forgot to write it. Here you have it for all I, for all agents. Okay. So yeah, so for the links between the notions of fairness, I said it when it's n proportional is equivalent to proportionality, and 2 proportionality is equivalent to envy-freeness. I'm just going to do the proof for this one. It's a very it's quasi immediate, but so this is the 2 proportionality. So for every set of agents of size 2, the utility I assign to my cake is better than the average utility. Then you take this and you make it go to the left, so you obtain this, and of course you multiply by 2 and you have this, which is just saying that for every I different than j, I prefers their piece of cake. So yeah, that is very immediate. But yeah, this is nice because you have a notion, K proportionality, that englobes the two notions. One that is very restrictive and free. You don't want anyone to be jealous of anyone, and one that is more relaxed, proportionality. And so you can quite imagine that K proportionality is like the in-between, and between something that is very restrictive and hard to obtain, and something that is less restrictive, but that will be easier to obtain. We will see after algorithm for having both envy-free cake cutting and proportional cake cutting, and we will see that having a proportional cake cutting is very easier in practice than having an envy-free cake cutting. Yes.
Yeah, so here you are I is strictly lower than J. Isn't it just different? Because I'm not sure that you.
Yeah, so you can just say for every I different than J. This is. Yeah.
Just for me, 2 proportionality implies envy-freeness, but it's stronger for me. Envy-freeness is 1 proportionality. So, you agree?
It's 2 proportionality. Because in the 2, you've got yourself and the person you're comparing.
Yourself.
Yes.
Okay.
Yes. So in the K proportionality, you include yourself from the set of agents. Yeah. So that's why. And yes, here I could have put different, but I think it's equivalent because when you have this. Yeah.
I is different. I plays a special role, so it's no longer equivalent.
Yeah.
Yeah, maybe I should have put different. But if you put different everywhere, it still holds.
Yeah.
So the equivalent still holds. So, but yes, you are right.
Where do you have backward application like?
Yeah.
Okay.
Yeah. Okay, and yeah, another theorem, yeah, envy-freeness implies proportionality. And again, the proof is very simple. So here you have envy-freeness, and if you just sum on every, so for I, if you just sum on every agent j, you obtain this. This does not depend on j, so this is equal to n times mu I of ci, and this is the sum for every j of mu I of cj, so the sum of every utility I allocate to every piece of cake, which is 1, because this is a partition of the cake, actually. And so you obtain the proportionality.
Does that also hold for K proportionality?
If envy-freeness implies K proportionality?
Yes. The same proof seems to hold, but I may be missing something.
Well, I think it still holds, yeah. I think envy-freeness implies K proportionality because here you sum on K, so you will have K here, and this is just the thing you see appear in the K proportionality.
Looks like it works.
Yeah, it works. What I think doesn't work is saying that K proportionality implies K plus 1 proportionality. I think there is no link between any K, but for K equal to 2, you are right, it implies that 2 proportionality implies any K proportionality.
It's not straight, but it's not really good.
Yeah, no, I think you're right. I'm convinced.
You have some comments.
Oh. Yeah, so okay, so what is yeah, so what François is saying in the chat is that K plus 1 K proportionality implies M times K proportionality, because when you have a set of K agents and another set of K agents and you add the two, then you will have 2 K agents and the proportionality will still work. That's what you were discussing. Okay, so yeah.
We agree.
Yeah, and so he says that in particular, 2 proportionality implies all the other one because of this.
But it means that if you only have some generic K proportionality, you don't necessarily have N proportionality.
Yes,
Okay, so
indeed. Oh. No, I cannot go back. Oh, I can go back. K means you share is better than the average of your work. Yeah. Yes. Okay. All right. Yeah, so theorem, an envy-free allocation always exists. This is true because we do not have direct measures. So that's why we supposed it before. It's because this does not become true if you have directs. And of course, a proportional allocation always exists because as envy-free implies proportionality, if you have an envy-free, you have a proportional allocation. But an equitable allocation does not always exist. This I won't do the proof because I saw it in an article and I didn't have the time to read the proof properly, but they just exhibit a counter example when there are 3 agents, I think. So they have like a measure of, they have 3 measures, and they show that with those measures, they cannot reach an equitable allocation. Yes, so now I don't want to spoil you. Yes?
Yeah, I don't know if it's something you're going to mention. Because could you have multiple envy-free allocations?
Yes, you can have several envy-free allocations. You not necessarily have a unique solution. And by the way, we will see an example with 2 agents where you could have several allocations.
It's very easy to have an infinity as long as you've got steady parts in your distribution. You can slide one way or the other.
Yeah, the question is more about.
Oh no, because the 0 is imposed.
No, it's not.
It's not necessarily imposed, but
can you have? I guess my question is: can you have envy-free allocations proportional allocation, where if you have two different virtually different utilities, sort of like
Yes.
I'm thinking of this in
Okay.
game
So
theory.
yeah. So when you do an envy-free allocation, you are not necessarily doing the optimal one, in the sense that in envy-free allocation, you ensure that no one is jealous of anyone else, but you do not ensure that you maximize the general level of happiness. Like
But you could have two different allocations which have two different scores.
Yes,
Okay,
yes, of course.
Okay,
and when we have two agents, I will show you that yes, you are right, and you could like do the algorithm in another way and have another
better allocation.
So yeah, so let's see the algorithm. First, I want you to try to imagine how you would do an allocation that is envy-free when you have only two agents. For like just 1 minute, try to think about it, and then if you want a clue, try to see the agents are with not having the same role. They have not symmetric roles. So does someone have an idea? Yeah.
If you look at the difference between your utility and the person in front of you, it starts at 0, ends at 0, so it has to cross 0 at some point. No,
your utility starts at 0 and
no, the difference
ends at 1
between you and the other person. At start, you're both at 0.
Yeah.
At the end, you're both at 1.
Yeah.
So the difference has to start at 0 and at 0.
Yeah.
So it crosses 0 at some point.
Yes.
And you can just cut there. You know you'll have the same
yes. Yes, you could. But here you will have exactly, this is for having an equitable allocation, right?
Sorry, yeah, this is true.
I think, yeah, this
bad.
is for equitable.
Try to give it a shot, stable voyage time. You try to build a chain of people that prefers the other slice to the other, and can be infinite. So at some point, you've got two people that want to swap their cake parts, and you just iterate until you prove that you cannot do it.
So this is quite the idea. I think when you have n agents, you will have an idea of swapping things. But when you have two agents, it's actually quite easier.
Everybody just, for every piece, you can just look who prefers that and give it to them.
So the thing is, here you are thinking as if there are already two pieces that are cut.
No, I'm thinking cutting the preference at the. Because if you've got.
So if you put a separation in the middle of the rectangle, and you move this rectangle, this separation, one becomes happier and the other becomes less happy, right? And
not necessarily, but because imagine agent 1 prefers the left and agent 2 prefers the right. Then you don't have to know. So the thing is,
but just for 2, yes, you just use domination. For each part, for each elemental of the cake, either it's preferred by X or preferred by Y. So you can have a part that is preferred strictly by the first player, a part that is preferred strictly by the second player, and you start with that, and then you slide a bit. So it's that kind of idea.
I think that could work, but this is still very complicated compared to a very simple solution. So the solution when you have two agents is just you ask agent 1, cut the cake so that you think every part is equal. So every part is 1/2, 1/2. And then you just ask agent 2 to choose their favorite part between the two. So imagine that agent 1 has cut the cake like this. And then imagine that agent 2 thinks that this part is greater than this one. Agent 2 will choose this part. And so they are not envious of agent 1 because they think this is better than this. And agent 1 chooses this because they think both parts are equal. So
it's a really shitty version of
it's a really, I think it's a really shitty version because as you said here, imagine that you ask agent 2 to do so. you could increase the level of happiness of both agents by doing this. But again, here we are not searching to maximize the utility of every agent. We just want no one to be envious of anyone else. But again, you could imagine that here you run the algorithm 2 times, one by asking agent 1 and one by asking agent 2, and maybe choose the best of both. But yeah, still in this allocation, you know that one agent will have at most utility 1/2. But that's the very easiest way to cut. Yeah. There is no really best of both.
Yeah, that was
you can combine the two results.
Because if you start by one, she'll have utility 1/2. Yes, that's what I was saying.
Yeah.
In here, you at most you will have one agent that will have at most utility 1/2.
You can maximize the utility of the winner.
Yes.
But the utility of the
yeah,
loser quotient is 1/2.
will still, yeah, I agree. Yes, yes. So the two chansons, yeah. But that I was just trying to say that if you run it 2 times, you can increase the general level, like the general happiness, but at the end, yeah, it will not
Somebody will be at 1/2.
Yeah, someone will still remain
And
at 1/2.
I guess, is there 2 questions? A better algorithm? And is there a way to define an optimal allocation?
Okay, so about optimality, I think there are some literature that try to, not only do an envy-free allocation, but one that is optimal, but it's actually hard to do. And so I think for 2, 3, maybe 4 agents, you have better algorithms than this one. But when you consider n agents, you will see that it's actually very difficult to obtain optimality. And so we are already happy if we have an envy-free allocation that works when you have an arbitrary number of agents.
I was thinking for 2 agents, and you have an allocation where no allocation would have given a better score to either player. While the
This
it may not exist. That's kind of part of the question.
I think it exists
Okay.
when you have to. I've seen literature talking about this, so I think it exists when you have 2 agents. And we have a comment. One of them, yeah. Okay, so 3 agents. You still have something that looks like this for 3 agents. So now you ask agent 1 to cut the cake in 3. And then you have two scenarios. Either agent 2 and agent 3 do not have the same preferred piece of cake. And so then imagine that agent 2 prefers this one and 3 this one. You just say, okay, you will have this one, you will have this one, and agent 1 gets the left part, and everyone is happy, not envious of anyone else. Or you have a more complicated scenario where both agents 2 and 3 prefer the same piece of cake. So imagine that they both prefer this one, and then that's where we have to work a little to ensure that no one envies anyone else. I won't make you try to guess what is the algorithm, because it's actually not intuitive for me. So the thing you say is you ask both agent 2 and 3 to trim this cake, this piece, so that the utility of the cuts is the same as the utility of their second favorite piece. So imagine that here, agent 2 says, okay, if I cut the cake here, this piece of cake has the same utility as my second favorite. So we could imagine that, for example, this is their second favorite, and they say that this equals this. And then you ask agent 3 to do the same. So imagine that for them, cutting like this is equal to their second favorite piece. And then you will have, once you have that, you choose to cut the cake like this. So you say, okay, you are cutting a bigger interval. So you cut this interval like this and like this. And then we can work with those 4 parts. So what happens is that you allocate this part to agent 3 because they allocate, they think that this is greater than this. Yes?
That's another question.
Oh, sorry. So for agent 3, they think that this is better than this and is better than this. So agent 3 is not envious of anyone else. Agent 2 is also not envious because for them, imagine that this was their second favorite part. They think that this and this is equal. And also they prefer those both parts to this one. So 2 is not envious as well. And agent 1 is also not envious because at the beginning they cut the parts equally. So for them, this is bigger than this, and this is equal to this. So at this stage, we have a partial allocation, and we have a remaining piece here. So the partial allocation is envy-free. And so we want to cut the remaining piece so that it's also envy-free. And because the measures are, I don't remember, are additive, thank you. Because the measures are additive, if we have an allocation that is envy-free and a second allocation that is envy-free, the sum will remain envy-free. Okay. Because if mu I of Ci is greater than mu I of Cj in the part of the cake and in the other part of the cake, the sum will still be greater than the sum of the 2. Yes?
I have a feeling there's another way of allocating which feels simpler, which should be, so agent 1 cuts in 3, gets left 1 slice. And then agent 2 can just cut the 2 slices in half and half according to agent 2, and have agent 3 choose one of the halves and one of the half. And it feels like you would sort of come back to the previous problem.
No, because in this setting, you could have agent 1 that is envious of one of the other agents. 2 and 3 won't be envious, but if you cut, you want to cut this and this, right?
Yeah. But
if you cut this and this, you could have one agent that will have a bigger part than one.
Agreed.
Yeah. So yeah, and also you could think of trim this only between 2 and 3, but you will have the same problem, is that, that agent 1 could be envious. So that's why this, you really need to cut it in 3 and allocate some parts to agent 1. So here you ask agent 2 to cut. The order, the person you ask is important. You need to ask the person that cuts it here, the bigger part, for it to work. If you don't do that, it won't work because this one could be envious. We will see why no one is envious at the end. And here you ask agent 3 to choose first. So at this point, you know that agent 3 will not be envious of anyone because they are not envious here. And here, as they choose first, they cannot be envious. Because, yeah, of course, we consider that everyone chooses according to their preference and is true, like is honest about their preferences. Then you ask agent 1, and agent 1 could be envious of agent 3 because they choose second. But remember that agent 1 thinks that this is greater than everything here. And so you can see that the green area here is smaller than this total part. So 1 will never be envious of 3, actually. And then agent 2, here they are not envious in this part because they did the cutting. And so for them, the 3 parts are equal. So 2 is not envious here and not here. So they are not envious to anyone else. So Yeah, for 2 and 3, the argument is that they are not envious here and here, so they won't be envious at all. And for 1 is that this part is still bigger than that this one, and that they cannot be envious of 2 because they chose before. Okay. Is it clear for everyone that no one envies anyone?
So, sorry, why is agent 2 not envious?
Because agent 2 did the cutting here.
Okay, okay.
And so that's why it's important that the agent that cuts is agent 2.
Okay, thank you.
Because they need to choose last, and here the person here needs to have to choose first, the green person. So the order here is really important, actually. Okay, so the algorithm for 3 quite generalized in when you have n greater than 3, but it starts to be more complicated. The reason is because here you only have 1 competitive piece of cake, like you have a competition. But when you have 4 agents, then you can start to have two pieces for competition, and then you will have to iterate the process. And when you iterate the process, you can lose the envy-freeness, and so you need to introduce swaps. So that and yeah, you need to introduce a permutation between the parts that you allocate, and this starts to get complicated. Honestly, I haven't looked in detail to the main to the algorithm, but it's an algorithm that uses several sub-algorithms where you can swap, and it starts to get really complicated. And it looks like this. So you have the main protocol, which is when you have a piece of cake, try to do a partial allocation. This just says that you will reduce the residue. And this is the protocol that you can call when you want to swap things, and you still have another and another here. It's a really complicated algorithm that I don't want to enter into detail, but just know that it's based on the same principle that you ask one agent to cut into equal parts, and then you do partial allocations, and then you do swaps. Yeah, and if you want to look at the algorithm, it's in this paper, a discrete embodied envy-free cake cutting protocol for any number of agents. There is also a video on YouTube where I think it's Mackenzie who explains the principle, but they don't go into big detail. But yeah, if you want to look at this, you just enter envy-free cake cutting protocol, and I think you will access the YouTube video if you're interested. Okay, so here we have seen envy-free algorithms. Yeah.
One quick question. Here the algorithms are cooperative in the sense that everybody, when they're supposed to cut properly or show their utility, they say so honestly. Does this sort of algorithm still hold if the agents are trying to cheat?
No, because if you are trying to cheat, then it doesn't hold. Those algorithm works because we consider that the people are honest, and actually it's proven that I think every algorithm, but in particular 2 and 3, the best strategy they can have is being honest.
Yeah, that's my question. Do we have one where basically the incentive is to work along?
No. In those algorithms, the best strategy is to be honest.
Even in terms of collections?
I don't know.
Because usually, if you only want to lie, it comes back.
Yeah.
But if you have multiple players that lie,
this I'm not sure, but yeah.
Asymmetrical is 3 people, for example. It's not clear if one can cheat by lying on the first cut, for example, or if that's going to come back and bite him in some cases. I
think for agent 1, they cannot cheat because they are sometimes they could earn more, but sometimes it could do not be.
They don't know the utility of the.
Yeah, that's it. If you don't know, and I think that you consider that you don't know the utilities of other players when you imagine this. But yeah, you could of course imagine scenarios where you know the utilities and see a coalition could work, but
There is a Fafan interaction.
We don't know it's false yet.
in the tree, no, can force the second player to have exactly and to have a better utility set, but she needs to know play. Yeah, that's it. So I think that in the model we consider that you don't know the other utility.
Right? You could, if you force the other cat utility 1/2, it decides which utility you get of the two.
I think what he imagined is that imagine you know the utility of the other person, you just cut where the other one is 1/2, 1/2, but here you cannot ensure that you will get the piece you prefer.
Minus epsilon, so you can control the parts you will choose.
Yeah, in that case, so, okay, I guess.
Oh, yeah, so you... Yeah.
Because otherwise you have...
yeah, so you can... Yeah. Okay, so it's not exactly 1/2, but it's 1/2 plus epsilon, so yeah. Okay. Okay. Yeah, so yeah, what I was saying is that, of course, when you have envy-free, remember that you also have a proportional allocation, because an envy-free allocation is proportional. But what if we only want proportionality? Is it simpler? The answer is yes, it's way easier to get. So here is an algorithm. Do I have the time? I think I will just, I will just explain quickly. You ask every agent, here it's player, but it's just because I copy-pasted agent, to cut the parts, to cut once, and to so that the ratio is n divided by 2 floor and divided by 2 fill. And so, for example, when you have 3 agents, the ratio will be 1/3, 2/3.
The utility.
Yeah, the utility ratio. So you ask every agent to cut the cake to have a 1/3 part and a 2/3 part, and then you sort them by the one who cut the more to the left, to the right, and then you do a recursive cut. So you order the player, and then the first n over 2 players will be on the left side, the second will be on the right side, and then you do it again until every player is assigned a unique, is only assigned to a part. Like you don't have 2 players assigned to the same part. Let's just see on an example where you have 3, so that we really understand why it's proportional. So imagine you ask, and this is what you get. So remember, for example, for C1, this is 1/3 and this is 2/3. Then you cut this, okay? You know that agent 1 will be assigned this part, and 2 and 3 will play on this part of the cake. So first, 1 is assigned this part because on the left part, the algorithm is done. And here again, you ask C2, you ask 2 and 3 to cut, and imagine you get this. So again, for C3 now, they consider that this is 1/2 and this is 1/2. Okay, so this is 1/2 of 2/3. Okay, and so here you assign this part to C3, because when you do the recursive thing, they will appear here. And then you assign this part of C2. And this, I claim that this is proportional. Why? For agent 1, it's easy. You know that this is exactly 1/3. For 2, you know that this is 1/2 of 2/3.
More than.
What?
Of more than 2/3. C2 wasn't at 1/3.
Yeah, you are right. It's 1/2 of more than 2/3, and even 1/2 of 2/3 is 1/3 of. So you know that this is bigger than 1/3, and this is even bigger because it's bigger than 1/2, bigger than 2/3. So this is greater than.
This feels like when you would really want to cheat out. The first player is always going to be envy
Yeah, so what I'm saying is that here, this is not necessarily envy-free. This is just a proportional allocation, but you can see that it's a way simpler algorithm and that it works.
Want to be C1.
Yes, you don't want to be C1, of course.
You want to place
Of
the
course.
cake so that your favorite part.
I
is
prefer
at the
the end.
Yeah, but that's the whole point of this notion, is that it's easy to get, but it's less convenient than envy-freeness. Yeah.
Easy in which sense? What is the complexity of the other and the complexity?
So that's my next slide. What about complexity? The first thing is we need to know how we measure complexity, which are the operations we take into account. And for this, we have something called the Robertson Web model, which you allowed two types of operation: cutting the cake to a point. For example, I ask an agent, cut the cake to the point 1/2, and they will give me the coordinates where they think the cake is cut into 1/2, and evaluate. So once I have a piece of cake, I go to an agent and I say, evaluate this part. And you can see that here in our example, we can describe every algorithm with those two operations. So here, when I do the algorithm, I say agent 1, okay, cut into 1/2, and this gives me the coordinate x where it is cut in 2. And when I allocate, here I say to agent 2, evaluate this, okay? So evaluate the interval 0x. And here I say to agent 2, evaluate the interval 1 minus x. And yeah, so we have those two. And then, of course, the operation here that is not taken into account is me comparing the evaluation. So there is, in this model, it is not taken into account. There is another model that takes into account the operation the mediator does. But in this one, you don't.
The eval, the x, here it works well, but if you have more than 2 agents, x is a portion, it's an interval, right? Or is it really from 0 to x? And if you want
it's from 0 to x. So I think here it's not 1 minus x. I think I should do.
sort of my question is,
Yeah.
should that be the interval, or should it be from 0 to the interval? And if you want to compute an interval, you need to do it twice.
Yeah, so if you compute an interval, you need to do it twice. Okay. So actually for this one, it should be 1 minus this evaluation. It's not this, it's 1 minus evaluation of 2x.
The eval, we assume, basically looks up the CDF measure.
Yeah. Yeah. So this is, it's quite like not contested in the literature. I've only seen one article that say, yeah, there is a model that takes into account the operation the mediator does to compare things, etc. But yeah, so this is the model we take into account when we talk about complexity. And so yes, so for proportionality with this model, there exists an algorithm that is big O of n log n. It's the one I showed before. And yeah, it has been proven that you cannot do better complexity. So this is quite the optimal algorithm you have that I showed. And for envy-freeness, cutting a cake is at least big O of n squared. This is a non-constructive proof. And the best algorithm we have is big O of n power n. And this algorithm is the one I explained before with the swapping thing, etc. So yeah, we quite think that this bound is not maybe optimal and that it could be raised, like that is not tight, because the literature and the people working on this field quite have the sense that it's very much more complicated than big O of n squared.
At least big O in the upper sense.
Yeah,
it's that you cannot do better than this, but they think that even this is too nice for the problem, that the real bound is bigger.
and you've got
and also there is
Which one? Oh, Okay, so this is the discussion before. Yeah.
So to compute the complexity, you assume in the previous slides,
Mm-hmm.
in the previous slide that first you cut and this has unit of complexity 1, and then you evaluate another unit of complexity. But for the envy-freeness algorithm you explained, we have to choose where to cut.
Yeah.
And so before cutting, I have to measure what if I cut here, what if I cut here, what if I cut here, or it's a function, so you can find the mean or the, but you don't have a cut that someone gives you and then you evaluate. You have to evaluate before doing a cut.
The cut operation has the alpha.
Yeah, I'm asking you to cut at 0.1/2, and I consider that you know exactly what is the 0.1/2.
Right.
The agent knows how to cut at.
Right. But in reality, I mean, it's an evaluation of a function because there is a function of x. No?
Yeah,
and,
but I agree that this model is.
It's a reverse CDF basically.
Right.
The two functions are basically evaluating the CDF or the reverse CDF. If I understand correctly.
Yeah.
Yes, but so you have to choose where to cut this.
Well, if you're doing cut at 1/2, you're looking at the CDF. You're looking at the 1/2 on the vertical axis.
Yeah. Okay. Yeah. You're right. Yeah.
So
it's very.
But again, if you're trying to cut a sub. Thing, you're actually doing 3 operations because you have to do the reverse CDF, reverse CDF, hit in the middle.
Probably, yes.
But it's the constant factor, so you don't care.
Yeah. That's the idea, but I agree that this model is not maybe
starting at 0 every time feels like you're overcomplicating it, but it's
probably. But this is the model used to measure complexity. And so here I put an open question. So how does the complexity of a k proportional allocation varies with k? Because here we see that when k is 2, it's very big. When k is n, it's okay. So does it vary with k? Is it increasing or not? This we don't know. It's an open question. And that's it. I think I finished. Yeah, that's it. Thank you.
Thank you.
Yes.
I have a question about the robustness of these protocols against manipulability. Something I worked with the transform and system. Maybe Agile may cheat about their evaluation of their utility to get a bigger part of what they will. Is this since been looked at in the literature?
So what I was saying before is that I think for envy-freeness, those algorithms are the best strategy you can do is being honest. So even if you cheat, it will not serve you. For proportionality, I don't know. I think proportionality algorithms, you could have things like that. And I know that, in the literature, it is studied. I've seen things that talk about this, but we have a comment. I don't know if he's answering you or just talking about something. So okay, so I don't know what he's talking about, but yes, in the literature there are some discussion about this. But for envy-freeness, I think the best strategy in this is being honest.
Sort of segue question. 2 questions, right? For the n agent, do you know how many pieces of cake everybody gets?
So
do you take into account the complexity of the cut, as in how many small bits I have?
That's a good question. I think for envy-free, they don't really try to minimize this number of cuts because it's already too complicated. But for proportional, that is a question. Can we have an algorithm that cuts the
First
minimal.
one does contiguous portions, right?
Yeah.
So that one already solves it. Everybody gets just one slice.
Yes. Yes. Yeah, but yeah, what I was saying is that in the proportional, you make imaginary cuts, you know, because you ask everyone to cut. And in this model, you consider that when you make imaginary cuts, you do not cut in real life. But if you cut, it would be a big number of cuts. And so, yeah, there is some literature that tries to cut. And in the model of proportionality, you consider that really there are imaginary cuts, and that at the end you only have k-1. But if you didn't allow that, yeah, you could want to optimize the number of real cuts you do, because you don't want the cake to be too scrambled.
Yeah, because with the end to the end to the end to the end,
Yeah,
it feels like everybody gets atoms.
yeah.
I was gonna ask
You don't get atoms. I think the complexity also comes from the fact that you swap species, and you can maybe swap a big amount of time. And so, yeah. But yeah, still in the envy-free, I agree that you have residues that get smaller and smaller, and that probably you have a bigger, but it's bounded. So I think what they mean by bounded is that at the end, the number of cuts is finite, I think.
Yeah, because you end the algorithm.
Yeah.
Other question, which is mine.
Yeah, just one remark, because I didn't hear you very well, but I think there was questions about the allowed operations from the point of view of complexity, and the fact that it assumes that you have access to the PDF of the preference or something like that. Or did I heard badly?
Yes, there was a question about this. Yes.
And yes, so what I was saying in the chat, that the allowed operations, in fact, are motivated by the applications that people have in mind when working on these problems, which are sharing the goods of the couple, for example, in the divorce procedures, or inheritance or stuff like that. And in fact, in this application, of course, you cannot have access to the PDF, but it's relatively easy to ask people to say, okay, for example, can you establish two shares that seem equal to you? And then you can ask the other person to for example, what is the share that you prefer? And that's more or less what the allowed operations in the model here account for.
You have a constraint in the 3 user case, where when you have agents 2 and 3 cutting the middle slice, they have to cut from the left side. So there's the order matters in the way you query. Not sure that was clear.
I didn't understand.
When you look at the 3 user case,
Yeah.
When agents 2 and 3 give where they would cut the middle slice,
Yes.
one of the cut has to be part of the other for it to work. So you do have in your query the idea that you're querying from the left. You ask them to not.
Yes. In that case, yes.
Okay. Just so, but I think all of those are basically equal.
But one other way to see it is to say an operation that you can do in practice, for example, is to say, okay, I have a moving knife. So I cut at angle 0, and then I take a moving knife and tell you, okay, stop me when you think that the 2 shares have equal value for you.
Yeah.
And that's an operation that can be quite intuitive for a real human agent.
I think it needs to be a bit more complex when you're cutting inside middle slices, because the 0 moves. But I think it comes down to the same thing. And
yeah, it's essentially the same. Yeah, it's essentially the same idea.
There's no added complexity. Yeah, my other question, but I don't want to hog the time, was, do we have any algorithms that are symmetric?
So every agent has the same role? Or-
Where if I change the role of agents, I get the same output.
Oh, so for envy-free, no. At least
This one
maybe,
is not.
yeah,
but-
maybe for envy-free, maybe when you have two agents, but I haven't looked at such thing. But for proportionality, you don't have, they have symmetric poles actually. So, except if you consider that you can move the zero.
Yeah, which.
But if you consider
my
that you do
question
not move the zero for proportionality, it's symmetrical.
Can you have sort of strategies where people are not fighting at the beginning to be in that role or to turn decay, where you know that those parameters will not change what you receive at the end?
I don't know. That's a good question, but I don't know. I don't think if people have really worked on moving the zero, but I should check.
We're assuming that the utility doesn't depend on other people's utilities,
Yeah.
which is fine.
Yeah.
But depending on your role, what you take away, your own utility will change. So you're still competing if you look at it as a competition, even if you're not depending on other people's utilities. The role you get will change your own utility. And I was wondering if there's a way to fade that out, but
Yeah.
we'll have to look into it.
Okay. Other questions? Okay, well, if no one has questions, thank you again.